This is part of introductory lectures on graphics, computer graphics, and we're starting with historical perspective out of a textbook we're using by Hennessy. And so we're talking about the evolution here, and some key things to note is the price changes and the performance and the rendering capabilities. Firstly, the prices. Originally, these were very expensive, tens of thousands of dollars for silicon graphics terminals. I remember in the 1990 it was approximately in a research lab, AI DuPont Children's Hospital and Applied Science and Engineering Lab. We just had one of these workstations, and it was very expensive. And then coming down greatly in price for the basics of what you would want to do in graphics to just on the order of hundreds of dollars. But now back up again for into higher numbers for high performance computer graphics, because now we have graphics processing units with a couple thousand CUDA cores. We'll talk about that, and you can use these graphics cards for what used to be considered supercomputing, and certainly for artificial intelligence applications nowadays. So the graphics card now is something completely different than it was originally. Not completely different, but certainly much more powerful. And then performance. So originally, and still somewhat to this day, people speak of pixels per second, vertices, right, per second of the primitives. And there's other benchmarks you can use too for performance. You can use floating point operations per second. But most typically, when you're talking about graphics, gaming, you want frames per second, some real-time kind of fast change of rendering. So frames per second, FPS, is what you want to get used to talking about. And then the third thing is what you could render. Originally, it was just wireframes to filled polygons and primitives. We call them primitives of different shapes, and you put them together. To now, everybody expects, and you get full scene texture mapping. So our computer graphics, the architecture and the hardware, has evolved from generating simple or from a simple pipeline for drawing wireframe diagrams to a highly parallel processing design with several deep pipelines. And so most of the students listening to this have heard of how the pipeline works. And advanced students, we design pipelines, parallel pipelines, superscalar processors. Well, a pipeline, if you haven't heard what it is before, you do certain things when you're executing machine instructions. And the simplest would be to fetch the instruction, then decode it, and then execute it. That's 3 stages of a machine pipeline, of a machine instruction cycle. And you can get up to the order of 50 stages in some of the pipelines on the CPUs over time. However, what we're talking about here is the GPU, the graphics processing unit on the graphics card, executing very specific tasks for graphics as part of the pipeline, and doing these things in parallel. So, yes, the GPU, the graphics processing unit, is different than a CPU. And for one thing, you can do some complex arithmetic floating point. We've talked about that in most courses that you've had with me to some extent. You can do a great deal of floating point on completely independent data in parallel for rendering and for the graphics. Then down below here we see whereas the CPU die area is dominated by cache memory, GPUs are dominated by floating point data path and fixed function logic. We also can use now, and often do, many people do, the graphics card for processing for things other than graphics at times. You can do artificial intelligence calculations. A lot of calculations you used to do in supercomputing where you need some parallelism, matrix vector kind of operations, or a variety of things you can do now. And so you see this acronym GPU for general purpose processing on a graphics processing unit. CUDA is by Embeddia, is really a dominating force in computer graphics card design. It's a very good company. You might want to look into them for employment or just what they're doing. They're always cutting edge. They have what I understand is a great corporate culture too. Would make a nice project, just somebody in introductory course, just to research just Embeddia, their culture, their products, their evolution, their market share. So CUDA is this C and C++ compiler libraries and runtime software to enable programs to readily access the new data parallel computation model and development applications. So you want to memorize that, what CUDA is, and look for that. Now we'll come back to that in a second here. Scalable GPUs are scaling the higher transistor counts by increasing the number of constant performance cores on a die rather than increasing the performance of a single core. So in advanced courses with me, you'll learn about scalability in parallel processing and grain size and how different grain problems can be parsed into fine grain versus coarse grain, and different parallel processing hardware that's suitable for that. And then here, for a comprehensive list and examples of current developments and applications that are accelerated by GPUs, visit CUDA Zone. So this is Embeddia, and I'd like you to take some time here. This is the last slide other than the references. So after this slide, then please go and understand what CUDA is. And then finally here you see in 2020, GPUs have over 2,000 CUDA cores. So you can think of these cores as not want to say simple, but they're not full CPU kind of cores, but they are complex in what they do, and they're dedicated to certain functions. And you get in the order of almost 2,500 now, so over 2,000 CUDA cores. And so take a look at the link to CUDA and Embeddia.